The latest AMS 2023 release includes a powerful new method for the prediction of accurate optical excitation energies, quasi-particle self-consistent GW-Bethe Salpeter Equation calculations, or qs-GW-BSE in short. Whilst yielding high-precision excited state energies in excellent agreement with spectroscopic data, the qs-GW-BSE calculations are computationally efficient and can be applied to large systems such as the photosystem II reaction center with roundabout 2000 electrons. In today's video, I want to show you how qs-GW-BSE calculations can be run with explicit spin-orbit coupling from the AMS graphical user interface. As usual, I will provide links to detailed step-by-step tutorial and info materials in the video description so we can focus on the bigger picture in the video. We follow in part the current qs-GW-BSE tutorial on the SCM website. We shall calculate the singlet-triplet gap of benzene. As in the tutorial, we chose the PBE functional with the TZ2P basis set. The numerical accuracy should be good, but the relativity should be spin-orbit. Now move on to the excitations panel and request spin orbit self-consistently. For a scalar relativistic calculation, we can get away with just 2 excitations, but with the spin-orbit coupling we need to up the number of excited states to span roughly as many excitations as without the spin-orbit coupling. Typically one needs 4 times as many excited states, so we request 8 excitations here. Finally, select BSE as the method before moving on to the GW settings. Enable the GW calculation by checking the quasi-particle energies checkbox and select qs-GW from the self-consistency drop-down menu. Now we do not need to worry about a possible starting point dependence of GW, also qs-GW usually provides the most accurate result. After saving and running the calculation, we can inspect the results in the output file. The results compare nicely to the experimental findings and are fairly close to the results without spin-orbit coupling, since the spin-orbit coupling is small for benzene. However, instead of a single triplet state, we now find 3 levels which are very close in energy. Those resemble the spin sublevels of a triplet state. So that's it for today. Make sure to check out the links below this video if you are interested in this or any other spectroscopic property simulation. I hope you found this useful, and as always, we're happy to answer any questions or comments below this video.